Somewhere out there tonight, a spacecraft the size of a small car is crossing through absolute darkness, 25.8 billion kilometers from the planet that built it. It is moving at 61,000 kilometers per hour. Its battery is dying. Its signal, when it reaches us, carries less power than a single photon of starlight landing on your closed eyelid. It set out for this journey in 1977, carrying a golden record on its side with Bach, whale songs, a mother's heartbeat, and the brainwaves of a woman falling in love. That spacecraft is still out there, fading, slowing down its whisper to Earth. But it will never, ever stop moving. Tonight we are going to follow it, past the moment it goes silent, past the next 40,000 years, past the death of our sun, and at the end of this video, you will understand exactly why a species on one small planet decided that the void deserved to know we exist. If you are new here, welcome. Stay until the end, because nobody told you the part after the last signal, the part that makes human history look like a footnote. The numbers are real. The timeline is already running, and it started in 1977. Now, let us get into it. Part 1. The collapse of now. There is a machine out there right now, drifting through absolute darkness, so far from Earth that the signal it sends us arrives with less power than a single photon of starlight landing on your closed eyelid. And we are still listening to it. We have been listening for over 46 years. That fact alone should stop you cold. Voyager 1 is currently about 25.8 billion kilometers from Earth. Let that number sit for a second, because just saying it doesn't really do anything useful for the human brain. 25.8 billion kilometers. Here's a better way to think about it. Light, which travels at roughly 300,000 kilometers every single second, takes more than 23 hours to make that trip one way. So when you think about the engineers at NASA who send a command to Voyager 1, they are not pressing a button and watching something happen. They are sending a message into a kind of temporal void, knowing the spacecraft won't even receive it until tomorrow, and if something goes wrong, they won't hear back for another day after that. The round trip is already beyond 48 hours. That's not a communication delay. That's a different relationship with time entirely. And what is actually receiving those commands? What are we talking to across all that distance and silence? Voyager 1 is roughly the size of a small car, if that car had a 10-foot wide satellite dish bolted to the top of it. It was launched on September the 5th, 1977, nearly half a century ago, and it was built with hardware that would be considered primitive by almost any modern standard. Its onboard computer has less processing power than the chip inside a digital greeting card, the kind that plays a little song when you open it. That comparison is not a joke, it is genuinely humbling, and yet this machine, this relic of 1970s engineering, has travelled farther than any object humanity has ever built. It has crossed the heliopause, the boundary where the sun's solar wind finally loses its grip on space, and it is now drifting through interstellar space, territory no human-made object had ever entered before it. It is the farthest thing we have ever touched, and we are still barely touching it. The signal that reaches us from Voyager 1 today is almost incomprehensibly faint. We're talking about something on the order of 1/10 of a femtowatt, which is 1/1000th of a millionth of a watt. To put that in perspective, the dimmest LED indicator light on a piece of consumer electronics uses roughly 1,000,000 times more power than the total energy arriving at Earth from Voyager's transmitter. To detect it at all, NASA's Deep Space Network, a system of enormous dish antennas positioned around the world in California, Spain, and Australia, has to point precisely at a region of sky, integrate the incoming signal over extended periods, and use sophisticated error correction just to pull usable data out of the noise. It is, in every meaningful sense, the most difficult listening operation in human history. And it is happening right now, continuously, every day. The data rate coming back from Voyager 1 is about 160 bits per second. 160. Your home internet connection, even a modest one, likely transfers data at speeds roughly 1,000,000 times faster than that. What this means in practice is that receiving a single scientific measurement from Voyager is not like streaming a video. It's more like receiving a telegram, slowly, from someone who doesn't know what the weather is like at your house and can't be reached by phone. Most of Voyager's instruments are already gone. The imaging science system, the camera that gave us those iconic pictures of Jupiter's storms and Saturn's rings, and that pale blue dot image of Earth, was shut down in 1990. Not because it failed, but because keeping it powered was a luxury the spacecraft could no longer afford. The cosmic ray subsystem, the plasma wave instrument, the magnetometer, one by one, over decades, systems have been powered down in a carefully managed process of triage that the mission team calls power management, and that the rest of us might simply call letting go. As of the early 2020s, only a handful of instruments remain operational, focused primarily on measuring the plasma, magnetic fields, and particle density of the interstellar medium around it. What remains is the barer skeleton of a working probe. Engineers at NASA's Jet Propulsion Laboratory describe the current situation as listening more than commanding. There are still occasional uplink sequences, instructions sent to adjust Voyager's orientation or to manage its power systems, but the relationship has fundamentally shifted. We're no longer driving this spacecraft. We are accompanying it at an ever-growing distance, catching fragments of what it tells us about a place no instrument has ever been. And here is the thing that should genuinely unsettle you. When a cosmic ray, a high-energy particle flying through interstellar space, struck Voyager 1's memory in 2023 and corrupted its telemetry stream, engineers on Earth did not know what had happened for months. They received garbled data that made no sense and spent weeks diagnosing the problem remotely, essentially trying to understand what was wrong with the computer by reading the nonsense it was outputting, with no ability to look inside it, touch it, or reboot it. The recovery required them to essentially reconstruct which part of the spacecraft's memory had been affected, write new code to work around the damaged section, and upload that fix across 23+ hours of space. It worked. Barely. But the fact that it happened at all reveals something important about the nature of this mission at this stage. Voyager 1 is surviving statistically, not structurally. There is no shielding against interstellar radiation. There is no redundancy for many of its remaining systems. Every single day it continues to function is a small statistical victory against the accumulated probability of failure, a victory that gets a little harder to win with each passing year. So we have this machine, 46 years old, running on hardware from a decade before the personal computer existed, receiving commands with a 2-day round-trip delay, transmitting data slower than a fax machine, vulnerable to single-particle corruption events it cannot protect itself from, and it is the greatest explorer humanity has ever built. These two facts are not in contradiction. They are inseparable, and the question of what happens to it next, and what it will keep doing long after it stops talking to us, is one of the most extraordinary stories in the history of science. Because here's what almost nobody focuses on when they talk about Voyager going silent. The silence is not the end. It is barely even the beginning. Part 2. The 2030s Event Horizon. The death of Voyager 1 will not be dramatic. There will be no explosion, no final distress signal, no cinematic moment of impact. What will happen instead is something almost more poignant than that. A gradual dimming, a slow withdrawal of response, like a voice at the end of a very long hallway getting quieter, not because anything is wrong, but simply because the distance has finally become too much. The power source keeping Voyager 1 alive is a radioisotope thermoelectric generator, a device that converts the heat from radioactive decay directly into electricity. It runs on plutonium-238, a material with a half-life of about 87.7 years, which means it loses roughly half its radioactive potency over that time frame. At launch in 1977, Voyager's RTG produced about 470 watts of power. Today it produces something closer to 240 watts, and it continues to decline, losing approximately 4 watts per year through a combination of nuclear decay and the gradual degradation of the thermoelectric components that convert that heat into usable electricity. 4 watts per year sounds trivial. Your average incandescent light bulb uses 60 watts. But inside a spacecraft operating at the extreme margins of its power budget, 4 watts is enormous. It is the difference between keeping a heater running or letting the fuel lines freeze. It is the difference between maintaining antenna orientation or watching the spacecraft slowly drift off axis in a way that can never be corrected. At this scale of power management, a single watt is not a unit of electricity. It is a unit of mission survival. The engineers who manage Voyager's power budget are doing something that has no real equivalent in everyday engineering. They are not designing a system with safety margins and backup reserves. They are operating a system that exhausted its safety margins years ago, making triage decisions about which functions continue to exist and which are permanently sacrificed. There is no bringing those systems back online. When a heater is turned off to save power, and the component it was protecting freezes and fractures in the minus 270-degree environment of interstellar space, that decision is final. There is no second chance, no redundant pathway, no contingency plan. You make the call, and you live with it across a distance that light takes a day to cross. Throughout the 1990s and 2000s, instruments were deactivated one by one in exactly this manner. The Plasma Science Instrument, the Cosmic Ray System, the Low Energy Charge Particle Detector. Each shutdown extended the mission's operational lifespan by a small amount, at the cost of reducing what the mission could actually learn. Every year, the team at JPL has essentially been making the same calculation. What is worth keeping, and what can we let go, and how long does that buy us? The current projection puts the end of Voyager 1's functional science operations somewhere in the early to mid-2030s. Not a specific date, not a countdown clock anyone can point to, but a range of years during which the remaining instruments will, one by one, fall below the power threshold needed to operate. After that, the transmitter itself may continue to function for a short additional period, sending carrier signals with no science data attached, a kind of technological heartbeat. And then, at some point that cannot be precisely predicted because it depends on factors including attitude stability and thermal behavior in a wholly unique environment, even that will stop. What makes this timeline genuinely strange is the question of how we will know. Because of the communication delay that now exceeds 46 hours round trip, there is no real-time monitoring of Voyager's health. The Deep Space Network receives telemetry, engineers analyze it, and they are always looking at a version of the spacecraft that existed nearly a day ago. By the time they know something has gone wrong, the event that caused it is already ancient history by the spacecraft's internal clock. In the final phase of the mission, as the power margin narrows to almost nothing, the line between a temporary anomaly and a permanent shutdown may not be immediately obvious. There may be a period, potentially weeks or months, where the signal has already stopped and no one is entirely certain whether it's gone for good or just interrupted. And then there is the antenna. Voyager 1's high-gain antenna must remain pointed at Earth with extraordinary precision in order to maintain communication. That pointing is managed by the spacecraft's attitude control system, which uses small thruster burns to keep everything aligned. Those thrusters require heaters to function. The heaters require power. As power declines, heater performance degrades, thruster reliability decreases, and the probability of antenna misalignment increases. If the antenna drifts and the spacecraft's attitude control system can no longer correct it, communication ends regardless of whether any other system is still functioning. The spacecraft could theoretically still be generating power, still running software, still measuring interstellar plasma, and be completely unreachable because the dish is pointed 3 degrees in the wrong direction. This is the most unsettling possible version of the end, and it is not an unlikely one. Voyager 1 could fall silent not because it stopped working, but because it stopped facing us. And out there, with no atmosphere, no friction, no corrective force of any kind, that misalignment would be permanent. The spacecraft would continue moving, continue functioning in some minimal sense, and become forever unreachable not through catastrophic failure, but through a slow geometric drift that no one on Earth could reverse. The spacecraft that goes silent in the 2030s, however it happens, will not be the same spacecraft that launched in 1977. It will be something that has been gradually transformed through decades of triage and loss, a succession of careful amputations performed across billions of kilometers of space, each one a small act of letting go in service of keeping something alive a little longer. The Voyager 1 that stops transmitting will be a ghost of itself in many ways, and yet it will have done something that no other object in human history has done, which is survive long enough and travel far enough to give us a direct measurement of the space between stars. And when the last signal fades and the engineers at JPL sit with the silence, knowing the spacecraft is still out there but beyond reach, they will be confronted with a question that no mission team has ever had to sit with before. What do you call something that is still moving, still intact in many respects, still carrying the golden record and the names of everyone who worked on it, still drifting outward at 61,000 kilometers per hour, but which you will never hear from again? Is it still a mission? Is it still yours? That question doesn't have an easy answer, and understanding why it doesn't requires understanding where, exactly, Voyager 1 is going and what it's going to encounter over the next several thousand years, none of which we will be alive to see. Part 3. The Power Fade. Nobody feels except NASA. Here is a strange way to think about energy. On Voyager 1 right now, every single watt of electrical power is a decision. Not in the vague sense that all engineering involves choices, but in the literal sense that someone at JPL sat down and determined that this specific system, consuming this specific amount of power, was worth keeping alive compared to every other system competing for the same shrinking budget. Energy, at this stage of the mission, is indistinguishable from knowledge, and the rate at which it is disappearing tells us something profound about the nature of long-duration space exploration that most coverage of Voyager never quite gets around to saying directly. Plutonium-238 decays slowly. That is precisely why it was chosen. With a half-life of 87.7 years, it releases heat at a rate that is predictable, stable, and long-lasting, ideal for a mission that was always intended to operate for decades. The decay process itself is not sudden. It does not run out like a battery. It fades, mathematically and smoothly, along a curve that engineers can model with high confidence decades in advance. By the time of Voyager's launch in 1977, mission planners already knew roughly what the power output would look like in the 2000s, the 2010s, the 2030s. They knew the machine would not last forever. They designed it to last as long as possible within those constraints. But plutonium decay is only part of the story. The thermoelectric converters that translate the RTG's heat into electricity, the actual mechanism by which thermal energy becomes usable power, have also been degrading since launch, and they degrade faster than the fuel itself. These converters work through a process called the Seebeck effect, where a temperature difference between two materials generates a voltage. The materials used in Voyager's thermoelectrics were the best available in the 1970s, but they were never designed for 46 years of continuous operation in deep space, exposed to radiation and extreme thermal gradients. They have been slowly losing efficiency throughout the entire mission, meaning the actual power output decline is steeper than nuclear decay alone would suggest. The result is that Voyager 1's power situation today is shaped by two simultaneous degradation curves, the nuclear decay curve, which is predictable, and the thermoelectric efficiency curve, which is somewhat less so. Together, they have reduced output from roughly 470 watts at launch to somewhere around 240 watts today, and the decline continues. 4 watts per year is the approximate current rate, though this figure is itself subject to revision, as the thermoelectrics continue to age in ways that are difficult to model precisely from Earth. What does this mean in practice? It means the mission team has been playing a very long, very slow game of priority triage for decades. The imaging system went first, in 1990, because visual documentation of interstellar space was deemed less scientifically valuable than in situ measurements of particle environments and magnetic fields. Heaters for various science instruments followed over the years: the planetary radio astronomy instrument, the photopolarimeter. Each deactivation was a permanent decision, made after careful deliberation across a communication channel with a round-trip delay that was already measured in hours by the time some of these choices were made. There is something philosophically significant about this process that tends to get lost in the technical details. When the mission team decides which instruments to keep running and which to shut down, they are not just making engineering decisions. They are deciding what humanity is allowed to know. They are determining which questions about interstellar space get answered and which do not, based on the available energy budget of a nuclear battery launched 46 years ago. The power budget of Voyager 1 is simultaneously a scientific resource allocation problem and a kind of ongoing conversation about the value of knowledge versus the cost of obtaining it. And the costs keep rising as the power keeps falling. Maintaining attitude control, keeping the antenna pointed at Earth, requires periodic thruster burns, which require heater power, which requires electrical power, which is running out. The decision to extend the mission by keeping science instruments running has to be weighed against the risk that the power used to run those instruments is power that could have been used to maintain attitude control for another few months. Every gram of science data comes at the cost of mission longevity. Every month of continued transmission costs something from the reserve that keeps the antenna aligned. The people making these calls are not working with unlimited time or perfect information. They are sending commands to a spacecraft that won't receive them for 23 hours, receiving telemetry that reflects conditions that existed yesterday, and making predictions about system behavior in an environment, interstellar space, that no other probe has ever occupied for this long. They are, in the most literal sense, flying blind at the edge of everything we know, with a power source that is slowly, irreversibly running out. And here is the thread that connects all of this back to the larger story. The reason these power budget decisions matter, the reason the specific rate of 4 watts per year carries such weight, is not just about Voyager. It is about what happens after the power runs out. Because the spacecraft does not stop when the power does. It keeps going. At 61,000 kilometers per hour, it keeps going for billions of years, through regions of space so remote and so far in the future that no human institution that exists today will be around to observe any of it. The power is running out. The journey is not. Every watt that has been saved through triage, every instrument that was sacrificed to extend the mission by a few more months, represents an additional fraction of data from interstellar space, data that, in some cases, we could not have gotten any other way. The slow power fade of Voyager 1 is not just a story of declining capability, it is a story of knowledge being extracted, molecule by molecule, from an increasingly hostile and inaccessible environment, right up until the moment when the machine that gathered it can no longer reach us to tell us what it found. What it found, it turns out, was not what anyone expected. Part 4. The 48-hour conversation with a dying machine. There is a type of communication that most of us have never had to think about, because everything we communicate with responds faster than we can notice. You tap a screen, a notification appears, you click a link, a page loads. Even a slow internet connection, in human perceptual terms, is essentially instantaneous. The entire architecture of modern communication is built around the assumption that the gap between sending and receiving is negligible. Voyager 1 has spent the last 4 decades systematically dismantling that assumption. The one-way signal travel time to Voyager 1 is currently more than 23 hours. This number has been increasing every day since launch, growing by approximately 3.6 seconds every 24 hours as the spacecraft continues to move away from us at 61,000 kilometers per hour. When you work out what this means for mission operations, the implications are disorienting in a way that is genuinely hard to internalize. The engineers who manage Voyager today are not controlling a spacecraft. They are having a very, very slow conversation with one. A conversation where every message takes nearly a day to arrive, and every response takes nearly a day to come back. A conversation, in other words, where the full round trip already exceeds 48 hours and will only grow longer with time. Think about what that actually means for day-to-day operations. If an anomaly develops onboard Voyager 1, a temperature reading that looks wrong, a thruster that doesn't fire correctly, a science instrument giving unexpected output, the mission team does not know about it for up to 23 hours after it happened. By the time they have diagnosed the problem and prepared a response, another 23 hours pass before the spacecraft receives their instructions. If their first attempt at a fix doesn't work, add another 48 hours for the next exchange. A troubleshooting conversation that might take minutes between two engineers sitting at the same desk takes days between Earth and Voyager. And by the time any command reaches the spacecraft, the conditions that prompted the command may have changed completely. This creates what you might call a temporal disconnect in mission management, a situation where the commands being sent are in some sense responses to a past that no longer exists. The spacecraft receiving an instruction today is not the same spacecraft that generated the telemetry that prompted the instruction. It has moved. Its internal temperatures have shifted. Its thrusters have consumed slightly more fuel. The feedback loop between observation and response has been stretched so far that it barely qualifies as a loop anymore. It is more like two parallel monologues happening simultaneously in different time zones, except the time zones are measured in days, not hours. The psychological dimension of this should not be underestimated. The people who have dedicated careers to this mission, who have spent decades developing intuitions about how this spacecraft behaves, building mental models of its quirks and tendencies, watching it gradually weaken year by year, are managing a relationship with something they cannot see, cannot touch, and cannot respond to in anything approaching real time. When the memory corruption event occurred in 2023, and Voyager began sending garbled telemetry, the team did not have the luxury of rapid iteration. Every hypothesis about what was wrong had to be translated into a command sequence, uplinked across 23 hours of space, and then evaluated against the results that came back another 23 hours later. The diagnosis took months. The fix required writing new code to route around a damaged memory segment and uploading it across the void. The entire process was a masterclass in patience as an engineering discipline. What this communication reality also means is that true real-time control of Voyager 1 has been effectively impossible for years. The mission team does not steer the spacecraft the way you might steer a drone or a robot on Mars. They plan ahead, they model outcomes, they write sequences of commands that the spacecraft will execute autonomously over extended periods, and then they watch the results come back later and adjust their plans accordingly. Voyager 1, in this sense, has been operating with a significant degree of autonomy for most of its mission, not because it has sophisticated onboard artificial intelligence, but because the communication delay makes any other mode of operation impractical. This makes Voyager 1 a very early prototype of something that future deep space missions will need to grapple with in a much more serious way. Any mission to the outer solar system, any probe sent to Neptune, to the Kuiper Belt, to targets beyond, will face communication delays that make real-time operation impossible. Any mission to another star, which even the most optimistic projections place decades or centuries in the future, will require fully autonomous systems capable of making complex decisions without any input from Earth. The 48-hour conversation we're having with Voyager right now is a preview of a challenge that will define the entire future of deep space exploration. And so far, the way we have handled it is through a combination of careful planning, patience, and a willingness to accept that control at extreme distances is largely an illusion. There is something almost meditative about this if you let yourself sit with it. Every command sent to Voyager 1 is an act of faith. You cannot verify it was received until the next day. You cannot know whether your response to a problem was the right one until the day after that. You're not flying a spacecraft. You're composing letters to a machine you once knew well, knowing it will read them tomorrow, in a place you have never been and cannot imagine, and that it will do its best to respond before whatever you wrote to it becomes irrelevant. In a way, that description applies to the Golden Record too, to the entire mission. It is all, at some level, a letter sent into a void with no certainty of arrival and no expectation of reply. The 48-hour conversation with Voyager 1 is just the most recent version of the same act of reaching out across impossible distance that has defined this mission from the beginning. But there is a fragility to this connection that goes beyond communication delay, a physical vulnerability that almost ended everything, not through system failure, not through power loss, but through a single particle of interstellar radiation hitting one specific transistor at exactly the wrong moment. Part 5. The Fragility Point. In 2023, Voyager 1 started lying to us. Not intentionally, not through any failure of its core systems, but because a cosmic ray, a single high-energy particle originating somewhere in the galaxy, travelling at a significant fraction of the speed of light, struck one of the chips in its flight data system computer and flipped a single bit of memory from 0 to 1. 1 bit. In a spacecraft with memory measured in kilobytes rather than gigabytes, one corrupted bit in the wrong location was enough to cause the flight data system to start sending garbled, meaningless telemetry back to Earth. For months, engineers received data that appeared to describe a spacecraft in a physical state that was internally contradictory and physically impossible. The numbers did not make sense. The patterns did not match any known fault mode. And for a mission team that had spent decades learning to read every quirk and tendency of this spacecraft, like a familiar handwriting, receiving output that looked like pure nonsense was, in a word, alarming. The fact that this happened 46 years into the mission in the interstellar medium is not a coincidence. One of the things Voyager has revealed about the space beyond the heliopause is that it is filled with galactic cosmic rays, high-energy particles accelerated by supernova remnants and other violent events throughout the galaxy, at levels significantly higher than inside the solar system, where the sun's magnetic field provides a degree of shielding. Think of the heliosphere as a kind of electromagnetic umbrella. Inside it, the sun's outward-flowing solar wind and its associated magnetic field deflect a meaningful fraction of the galactic cosmic ray flux, reducing the radiation dose that objects inside the solar system receive. Outside it, that protection is gone entirely. Voyager 1 has been operating in a fully exposed, elevated cosmic ray environment since it crossed the heliopause in 2012, and every single day it spends in interstellar space is another day of cumulative radiation exposure with no possibility of shielding and no means of repair. The memory corruption event of 2023 was a demonstration of just how thin the margin for continued operation has become. The team at JPL spent weeks diagnosing the problem through a communication channel with a round-trip delay of nearly 46 hours. Every hypothesis had to be formulated, translated into a diagnostic command sequence, transmitted across 23 hours of space, and then evaluated against results that took another 23 hours to return. They had to figure out, without being able to directly inspect any hardware, without being able to run a physical diagnostic, without being able to look inside the machine in any direct sense, which specific section of memory had been corrupted and how badly. It was fault diagnosis conducted entirely through inference, across a time-delayed channel, on hardware built before most of the engineers working the problem were born. The eventual solution was extraordinary in its complexity and remarkable in its execution. Engineers identified which memory addresses were affected, determined which data processing pathways depended on those addresses, wrote entirely new software to reroute the relevant functions around the damaged sections, and uplinked the patch to a spacecraft 25 billion kilometers away. The process required not just understanding what had gone wrong, but essentially reimagining how the spacecraft's software was organized, working within the severe constraints of a system with kilobytes of available memory and a processor running at speeds that would be laughable by any modern standard. And then they sent it across the solar system and into interstellar space and waited 23 hours to find out if it worked. It worked. Voyager resumed sending coherent data. The mission continued. Somewhere in a JPL conference room, there was almost certainly a very long exhale. But here is what that recovery actually revealed. And this is the part that deserves more attention than it typically gets. It revealed that the spacecraft was able to be saved this time through a combination of engineering brilliance and something that honest people at JPL would probably call good fortune, because the corruption happened to affect a section of memory that could be worked around. The damage was in a place where a software patch could substitute for the lost function. But what if it had been a different chip? What if the cosmic ray had struck the attitude control system instead? The system responsible for keeping the antenna pointed at Earth? What if it had hit the transmitter hardware directly, or one of the circuits managing power distribution from the RTG? There is no universal recovery procedure for random hardware damage in a 46-year-old spacecraft operating 25 billion kilometers beyond the reach of any possible physical intervention. The recovery in 2023 was not evidence of robustness. It was evidence of luck working in combination with skill. Those are not the same thing, and conflating them would be a disservice to the honesty the mission deserves. This raises a question that is uncomfortable but genuinely important. How many similar events have occurred over the course of the mission that were smaller, subtler, and effectively undetected? Cosmic rays do not send advance notice. A bit flip in a non-critical memory location might produce an anomaly that falls below the threshold of detection, or that mimics normal hardware aging behavior closely enough to be attributed to something benign. The mission team monitors telemetry carefully and with extraordinary expertise, but they are reading 160 bits per second of data from a spacecraft running software written in the 1970s, and they cannot inspect the hardware directly. They cannot open the box. They can only read what the box tells them, and a box with corrupted memory may not report its own corruption accurately. The question of how much silent degradation has accumulated in Voyager's systems over 46 years, how many micro-corruptions have quietly shifted its behavior in ways too small to isolate individually, is not a question anyone can answer with confidence. It may not be answerable at all. What we can say is that Voyager 1's continued functioning is not primarily a testament to the robustness of its original design, though that design was genuinely extraordinary for its era. It is a testament to the extraordinary sustained care of the people who have maintained it across nearly 5 decades, and to the statistical improbability of all the critical failures that could have ended the mission but have not. The spacecraft survives on the right side of a probability distribution that grows narrower every year. The margin between continued operation and permanent silence is not widening. It has been narrowing since launch day, and it will continue to narrow until the narrowing is complete. Sit with the distance this machine has travelled, 25.8 billion kilometres, and consider what it means that something so fragile, so vulnerable to a single errant particle, so dependent on a power source measured in watts, and declining by 4 of those watts every year, has made it this far. Every kilometre of that journey was a small statistical gamble. Every year of continued operation was a quiet miracle of probabilities falling on the right side. And through all of it, the spacecraft was not becoming more capable or more resilient. It was becoming more worn, more exposed, operating ever closer to its absolute limits in an environment that is actively hostile to the kind of electronics it was built from. There is something that deserves to be said plainly about this fragility, because it tends to get lost in narratives that emphasize triumph and achievement. We did not send an indestructible monument into interstellar space. We sent a car-sized collection of 1970s circuit boards, thermoelectric generators, gold-plated copper wire, and magnetic tape, and we watched it survive for nearly half a century through a combination of inspired engineering, constant vigilance, careful triage, and a statistical luck that could have run out at any point along the way. That is a more honest story than the clean narrative of technological triumph. It is a story about how much a group of people were willing to pay attention, and for how long, and what that sustained attention produced in the face of accumulating odds. Because the distance this spacecraft has already covered, and the incomprehensible distance it will cover after the last signal fades, is not the product of any single act of engineering genius. It is the product of 46 years of people refusing to stop paying attention to a machine that was getting harder and harder to hear. That is what the 2023 recovery actually demonstrated, more than anything else. Not that Voyager 1 is tough. It is not particularly tough. But that the people listening to it are extraordinarily good at their jobs and extraordinarily committed to the act of listening itself. The machine is fragile. The attention has been relentless. And in that gap between the two, an object launched nearly half a century ago has managed to become the farthest thing humanity has ever touched. Still whispering, still transmitting, still telling us what it finds in the space between stars. What it has found out there, it turns out, overturned decades of assumptions about the structure of the universe at the very edge of everything we call home. And that story is stranger and more beautiful than almost anyone expected. Part 6. The interstellar medium is not empty. Before Voyager crossed into interstellar space, the prevailing scientific understanding of what lay beyond the heliopause could be summarized fairly simply: not much. The space between stars was assumed to be, for most practical purposes, empty, an extremely low-density medium of gas and charged particles, smoothed out by the enormous distances involved, without significant structure or organization on the scales relevant to a single spacecraft's journey. The word that kept appearing in descriptions of the interstellar medium was uniform. Scientists used it confidently, repeatedly, as though the question had already been settled. We thought we knew what waited out there. We thought Voyager would cross the boundary and find a kind of cosmic background hum, featureless, diffuse, unremarkable, a void that confirmed what we already assumed. We were wrong in the most interesting possible way. When Voyager 1 crossed the heliopause, the formal boundary where the sun's influence ends and true interstellar space begins, the instruments that remained operational detected something that took years to fully characterize. The interstellar medium is not a uniform background. It is structured. It has density variations, organized turbulence patterns, and plasma oscillations that carry encoded information about events that happened hundreds of thousands or millions of years ago, originating from sources distributed across the galaxy. The picture that emerged from the data was nothing like the smooth, featureless medium the models had predicted. It was more like arriving at what you expected to be a still pond and discovering it was a river, not a chaotic, churning torrent, but an organized, layered system of currents and eddies moving on scales that dwarf anything in the solar system. The interstellar medium has structure the way weather has structure. It is not random. It is complex. And Voyager 1, with its 1970s instruments and its dwindling power budget, became the first object in human history to measure that complexity from the inside. The specific instrument responsible for some of the most striking discoveries was the Plasma Wave Science Instrument, a system designed to detect oscillations in ionized gas by measuring the electric and magnetic field variations associated with electron density waves. Think of it like this. When you drop a stone into water, the ripples that spread outward carry information about the stone, its size, its weight, the force with which it hit the surface. Electron density waves in plasma behave similarly. They propagate through the ionized gas of the interstellar medium, the way sound waves propagate through air, and the characteristics of those waves, their frequency, their amplitude, their direction of travel, carry information about the conditions that generated them and the medium they are travelling through. When Voyager's plasma wave instrument detected these oscillations, it was not just measuring a local phenomenon. It was in a very real sense listening to the interstellar medium tell its own history. What the measurements revealed about density was unexpected. The interstellar medium immediately surrounding Voyager 1 is denser than the pre-crossing models had predicted. Not by dramatic orders of magnitude, not 10 times denser or 100 times denser, but measurably, meaningfully denser, in ways that the standard models of the local interstellar environment did not anticipate and cannot fully explain without invoking additional physics. The discrepancy is not large enough to overturn the basic framework of our understanding, but it is large enough to demand explanation. And the explanation that has gained the most traction among researchers points towards something genuinely extraordinary about the neighbourhood our solar system currently occupies in the galaxy. Our solar system sits inside a structure called the local bubble, a vast, roughly elongated cavity in the interstellar medium that extends for hundreds of light years in multiple directions. This bubble was not always here. It was carved out by a series of supernova explosions over the past few million years, perhaps a dozen or more massive stars reaching the end of their lives and detonating in rapid succession, blasting enormous quantities of hot, ionized gas outward and sweeping the surrounding interstellar medium into a compressed shell at the bubble's edges. The interior of the bubble, where our solar system currently resides, is filled with hot, low-density plasma, the residue of those ancient explosions still cooling, still expanding slowly outward. The edges of the bubble, where the expelled material is piled up against the surrounding denser interstellar medium, are regions of compression, turbulence, and elevated density. Voyager 1, in crossing the heliopause, may be sampling the inner edges of this compressed boundary region. The higher-than-predicted density it detected, the organized turbulence patterns, the structured plasma oscillations, these may all be signatures of the local bubble's walls, the fossilized pressure waves of supernovae that detonated millions of years before our sun even formed. When the plasma wave instrument picks up an electron density oscillation, it may be detecting a ripple that was set in motion by the death of a star that no longer exists, propagating through the interstellar medium for millions of years before a small machine from the third planet of an unremarkable yellow star happened to drift through and measure it. Say that out loud for a moment. Voyager 1, carrying beck and whale songs and the brainwaves of a woman thinking about the cosmos, is drifting through space that was physically shaped by stellar explosions that predate the formation of our solar system. The structure it is measuring is not a local, incidental feature of the patch of space it happens to be crossing. It is a feature of galactic history, encoded in the density and motion of interstellar plasma, still propagating, still evolving, billions of years after the events that created it. Every data point the plasma wave instrument returns is a measurement of something that happened so long ago that the light from those supernovae has long since travelled across the observable universe and faded below any possible detection threshold. The events themselves are gone. Their consequences are still here, written in the density of space, and Voyager is reading them. Space, understood this way, is not empty. It is a medium with memory. It retains the imprint of events across timescales that human intuition cannot navigate directly. The interstellar medium remembers stellar deaths that occurred before Earth existed. It carries pressure waves from explosions that happened before the sun ignited. It is a physical record of galactic history, and Voyager 1, drifting through it at 61,000 kilometers per hour, is the first instrument we have ever placed inside that record to take direct measurements. This reframing matters enormously for understanding the journey Voyager will continue after the last signal fades. When we picture the spacecraft drifting through interstellar space in silence, for 30,000 years crossing the Oort cloud, for 40,000 years approaching the red dwarf Gliese 445, for billions of years beyond that, it is tempting to imagine it moving through nothing, through pure absence, through a void so complete that the word emptiness barely covers it. But that picture is wrong. Voyager 1 is moving through a structured environment. It is moving through a medium that has density gradients and magnetic field variations and plasma oscillations, carrying the encoded signatures of ancient stellar events. It is moving through a place that has, in the loosest but most accurate sense of the word, weather. Not weather you could feel or see or survive in, but organised variation in physical conditions, currents of slightly higher density plasma, regions where the magnetic field is stronger or differently oriented, pressure differentials operating on scales of light years. The interstellar medium is not a backdrop, it is a terrain. And Voyager 1 will be interacting with that terrain passively, without instruments to measure it, without a transmitter to report back, for timescales that make the entire operational period of the mission look like a rounding error. The 30,000 years of Oort cloud crossing will happen inside this structured medium. The 40,000-year drift toward Gliese 445 will happen inside this structured medium. Every billion years of continued travel will carry the spacecraft through regions shaped by the history of the galaxy, through the remnants of stellar deaths, through the edges of ancient supernova bubbles, through the quiet, organised complexity of a medium that we spent decades assuming was simply not there. We thought it was uniform. We thought we knew. And then a 46-year-old spacecraft with less computing power than a greeting card drifted past the edge of our solar system and started sending back data that rewrote the picture entirely. The universe beyond the heliopause is not empty. It is full of history. It is full of structure. It is full of the memory of things that happened long before we existed to wonder about them. And the boundary between our solar system and all of that, the wall between what the sun owns and what the galaxy owns, turned out to be something far more dramatic, far more physical, and far more strange than anyone had predicted. What Voyager found when it actually crossed that line was not a gradient, it was a collision. An understanding that collision changes everything about how we think about the solar system's place in the universe. Part 7. The heliopause was not a border. The theoretical models of the heliosphere, the bubble of solar wind that surrounds our solar system and separates it from the interstellar medium, predicted a relatively gradual transition at its outer edge. The physics seemed straightforward enough. As solar wind particles travel outward from the sun, they lose momentum progressively. They slow down, they cool, they spread out across an ever-increasing volume of space, their pressure dropping with distance, until eventually they no longer have enough force to push back against the incoming interstellar medium. At that point, the model said, the solar wind would simply fade, gradually, gently, over a broad region that might span hundreds of astronomical units. The heliopause in this picture was less a wall and more a shoreline where the tide goes out slowly, the boundary between solar influence and interstellar space dissolving across such a wide zone that calling it a boundary at all was almost a figure of speech. The transition would be diffuse, extended, unremarkable in its structure, if extraordinary in its location. Voyager 1 crossed the heliopause in 2012, and the transition was shockingly abrupt. The data did not show a gradual fade. It showed a near instantaneous change, a crossing so sharp that it registered clearly in multiple instruments almost simultaneously. One moment Voyager was in the heliosheath, the turbulent outer region of the solar bubble, where decelerated solar wind churns against the incoming interstellar material. The next, essentially, it was somewhere else entirely. The solar wind particles that had been Voyager's constant companions for 35 years essentially vanished. The galactic cosmic ray flux, the high-energy particles from across the galaxy that the sun's magnetic field had been partially deflecting, increased dramatically and almost immediately, jumping to levels that confirmed Voyager was no longer inside the sun's electromagnetic protection. The temperature of the surrounding plasma dropped. The density increased. The character of the magnetic field changed. Everything changed, not over hundreds of astronomical units as the models predicted, but over a transition zone so narrow that its thickness, in astronomical terms, was almost negligible. This was not a gradient. This was a wall. What Voyager had encountered was a compressed boundary layer, a region where the pressure of the interstellar medium pushing inward from outside had compressed the outward flowing solar wind into a relatively thin interface zone, like the skin of a soap bubble under external pressure. The solar system, it turned out, does not dissolve gently into the galaxy. It ends. There is a place where it stops, defined not by a smooth fade but by a dynamic pressure equilibrium between two different physical regimes, the sun's outward blowing wind on one side and the surrounding interstellar medium on the other, and that equilibrium produces a boundary that is, by the standards of space physics, remarkably well defined. The scientific community spent years working through the implications of the crossing data. Some of the debate focused on timing and instrument interpretation. Voyager 2, which crossed the heliopause in 2018 at a different location and a different angle, provided a second data point that complicated some of the simpler interpretations of the first crossing. But one finding from Voyager 1's data consistently surprised researchers, regardless of how they approached the analysis. The magnetic field behavior at the boundary was not what anyone expected. The models had predicted a chaotic transition zone where the sun's magnetic field and the interstellar magnetic field mixed turbulently, their different orientations producing a messy, disordered region of field lines, crossing and reconnecting and generally behaving in the complicated way that magnetic fields do when two different magnetized plasmas collide. What Voyager found instead was a magnetic field that changed in direction, as expected, but remained surprisingly coherent and well organized across the transition. The interstellar magnetic field on the other side of the heliopause, at least in the region Voyager crossed, appeared to be smoothly ordered rather than chaotic. The field lines were running in a consistent direction. The transition, while sharp in terms of particle populations and density, was not the magnetic chaos the models anticipated. This is the kind of result that makes plasma physicists genuinely excited and also genuinely uncomfortable. It means the models of how stellar wind bubbles interact with the surrounding interstellar medium are missing something. The physics that produces a sharp, coherent boundary rather than a turbulent mixing zone is not fully captured by the standard theoretical framework. Something about the way the sun's heliosphere terminates, some aspect of the pressure balance, the magnetic geometry, or the plasma dynamics at the interface, is not yet understood well enough to predict from first principles. Voyager 1 did not just confirm a theory about the heliopause, it produced data that the existing theories cannot fully explain, and there is currently only one spacecraft in interstellar space capable of providing the in situ measurements needed to resolve the question. The sharpness of the heliopause transition also carries implications that extend beyond the specific structure of our own solar system's boundary. If the interaction between a stellar wind bubble and the surrounding interstellar medium produces a sharp, compressed boundary layer rather than a diffuse gradient, this has consequences for how we think about stellar systems in general. Every star with a significant stellar wind, which is most stars, produces a heliosphere-like bubble called an astrosphere. These astrospheres are in constant dynamic interaction with the interstellar medium around them, and if the interaction is sharper and more energetic than the smooth gradient models implied, then the physics of that interaction, the way particles are accelerated at the boundary, the way magnetic fields are organized and compressed, the way the bubble responds to variations in the surrounding medium, is more interesting and more complex than we previously understood. Our solar system, in other words, is not a passive island drifting through a calm sea. It is a dynamic structure actively colliding with its environment, defined by a boundary that is maintained by a continuous pressure balance and shaped by the specific conditions of the galactic neighborhood we currently occupy. The heliosphere is not a fixed object. It breathes, in a sense, expanding and contracting in response to variations in solar activity, in response to density changes in the interstellar medium, in response to the slowly shifting conditions of the local bubble that surrounds us. The boundary Voyager crossed in 2012 is not the same boundary that existed 1 million years ago when the solar system was in a different part of the galaxy, and it will not be the same boundary that exists 1 million years from now. There is a physical intuition that helps make sense of all this, and it starts with movement. The heliosphere is not sitting still inside a stationary interstellar medium. The Sun orbits the galactic center at roughly 220 kilometers per second, carrying the entire solar system, every planet, every moon, every comet, every spacecraft we have ever launched, along with it. As it moves, the heliosphere pushes through the interstellar gas and dust, the way a bubble moves through water. The leading edge, in the direction of the Sun's motion through the galaxy, faces the incoming interstellar medium head-on. It is compressed by what physicists call ram pressure, the dynamic pressure exerted by the relative motion between the bubble and the medium it is moving through. The trailing edge, by contrast, is elongated into a long tail stretching out behind the direction of motion, less compressed, more diffuse. The heliosphere is not a sphere. It is an asymmetric structure, blunt on one side and extended on the other, shaped by its own motion through the galaxy. Voyager 1 crossed the leading edge. It hit the most compressed, most dynamic, most sharply defined part of the entire heliopause, the region where the ram pressure is highest and the boundary is thinnest. The fact that even this most extreme version of the boundary was coherently organized rather than chaotically turbulent makes the result more surprising, not less. If anywhere in the heliopause was going to produce the disordered mixing zone the models predicted, it was the leading edge, and it did not. What Voyager found when it crossed that boundary changed in subtle but important ways how we understand the solar system's relationship to the galaxy. We are not isolated from the interstellar medium. We are in active, continuous dynamic interaction with it. The boundary between what the Sun owns and what the galaxy owns is real, and it is sharp, and it is maintained every moment by the balance of pressures on either side of it. And Voyager 1, the only object humanity has ever placed in true interstellar space, crossed that boundary 13 years ago and is now moving away from it at 61,000 kilometers per hour, deeper into the structured, memory-laden medium of the space between stars. It is heading now toward a region we've never seen, a region so large that the word enormous does not begin to cover it. A region we believe exists because the mathematics of the solar system's formation requires it to exist, and because the orbital behavior of certain comets is consistent with objects originating there, but which no telescope has ever directly imaged, and no probe has ever entered. The crossing of the heliopause was the end of the solar system as most people think of it. What comes next is the solar system as it actually is, vast beyond any intuitive reckoning, extending into the dark for distances that will take Voyager 30,000 years to cross. And 30,000 years, it turns out, is where the story really begins to get away from us. Part 8. The Oort cloud problem. Here is a number that will not mean anything to you the first time you hear it, and then will slowly start to become genuinely alarming. The Oort cloud, the theorized outermost region of the solar system, extends from roughly 2,000 astronomical units to somewhere around 200,000 astronomical units from the Sun. An astronomical unit is the distance from the Earth to the Sun, approximately 150 million kilometers. It is the unit astronomers use when regular kilometers become too small and unwieldy to be useful, the way you stop measuring a cross-country road trip in centimeters. Voyager 1 is currently about 165 astronomical units from the Sun. To reach the inner edge of the Oort cloud, it needs to travel to 2,000 astronomical units. To cross the entire structure completely and emerge on the other side, it would need to travel to 200,000 astronomical units. Take a moment with those numbers. Let them settle. Because the gap between where Voyager is right now and where the solar system actually ends is so large that everything we have celebrated about this mission, every record broken, every boundary crossed, every billion kilometers logged, represents less than 0.1% of the total journey ahead. At its current speed of 61,000 kilometers per hour, Voyager 1 will reach the inner edge of the Oort cloud in roughly 300 years, not 300 days, not 300 months. 300 years from now, in approximately the year 2325, the spacecraft will begin entering the theoretical inner boundary of the structure we consider the solar system's outermost region, and it will take approximately 30,000 years to traverse the full extent of that structure and emerge on the other side. 30,000 years. This is the number that starts as an abstraction and becomes, if you stay with it long enough, something closer to vertigo. For comparison, consider what 30,000 years actually encompasses in human terms. The entirety of recorded human history, from the earliest cuneiform tablets pressed into clay in ancient Mesopotamia, through the construction of the pyramids, through the rise and fall of every empire whose name you recognize, through the birth of every major religion, the invention of the printing press, the Industrial Revolution, the discovery of electricity, the moon landing, the internet, everything that has ever been written down or remembered or passed from one generation to the next, spans approximately 5,000 to 6,000 years. Voyager 1 will spend 6 times that entire accumulated span of human civilization just passing through the Oort cloud. 6 times everything we have ever done, recorded, built, or remembered, and it will still be inside what we technically call the solar system for the duration. Let that restructure your sense of scale for a moment, because it needs restructuring. When most people think about the solar system, they think about the planets. Maybe they extend their mental map to include the asteroid belt, or Saturn's rings, or the Kuiper belt where Pluto lives. The solar system, in the popular imagination, is a relatively compact neighbourhood, something that fits on a poster, something you can summarise in a diagram. The reality is so much larger than that diagram that the diagram is essentially a lie of omission. The solar system does not end at Neptune. It does not end at Pluto. It does not end at the Kuiper belt. It extends outward for another 200,000 astronomical units into a region so vast that the fastest spacecraft humanity has ever built will need 30,000 years just to cross it. And here is the detail that should truly recalibrate your sense of what this mission is, what science knows, and what it does not. There is no telescope in existence today, or seriously planned for the foreseeable future, that can directly observe the Oort cloud. We have never seen it. Not one single comet-like body within it has ever been directly detected and confirmed in its natural location. Every image ever taken of the sky, from every observatory on Earth and in space, from the Hubble Space Telescope to the James Webb Space Telescope, has failed to directly capture a single object residing in the Oort cloud. Our confidence in its existence comes entirely from indirect evidence, primarily the orbital behaviour of long-period comets, those visitors that appear in the inner solar system on trajectories that bring them close to the Sun once every thousands or millions of years. These comets arrive from all directions, not concentrated in a disk or a plane, which is consistent with a roughly spherical reservoir at enormous distances. The statistics of their orbits point toward an origin region that matches what Jan Oort predicted, but the region itself has never been seen. The Oort cloud is inferred, not observed. It is a theoretical object demanded by the physics of solar system formation and supported by the mathematics of cometary dynamics, but confirmed by 0 direct measurements. When Voyager 1 eventually enters it in 300 years, it will become the first human-made object to physically enter a structure we have never directly seen and cannot currently see. It will be travelling through a theoretical prediction, albeit a very well-supported one. The theoretical picture, developed primarily from the work of Dutch astronomer Jan Oort in the 1950s, describes the Oort cloud as a roughly spherical shell, or more accurately, a nested series of shells transitioning from a flattened inner disk to a more spherical outer region, containing somewhere between 1 trillion and several trillion icy bodies. These are the leftovers of the solar system's formation, planetesimals that never coalesced into planets, primitive icy objects that were gravitationally scattered to extreme distances during the chaotic early period, when Jupiter, Saturn, Uranus and Neptune were migrating to their current orbital positions, their gravitational influence reshaping everything in their path. These scattered objects drifted outward to the cold, distant reaches where the Sun's gravity weakened to nearly nothing, and there they have remained for 4.5 billion years, moving so slowly in their vast orbits that a single trip around the Sun might take millions of years. These objects occupy a region so enormous and so sparsely populated that the average distance between neighbouring Oort cloud bodies may be measured in billions of kilometres. Even with 1 trillion or more objects distributed through the structure, the cloud is so immense that it is effectively empty from any practical standpoint. The probability of Voyager 1 colliding with or even coming meaningfully close to any Oort cloud object during its 30,000-year crossing is, for all practical purposes, 0. The spacecraft will pass through a region containing trillions of objects and almost certainly never come within 1 billion kilometres of any of them. The Oort cloud is, paradoxically, simultaneously the most populated region of the outer solar system and one of the emptiest places imaginable. The outer boundary of the Oort cloud, those 200,000 astronomical units, sits at approximately 1/3 of the distance to Alpha Centauri, the nearest star system to our Sun. This is not a coincidence. It is the physical limit of solar gravitational dominance, the distance at which the Sun's gravitational pull weakens to the point where objects are as likely to be perturbed away from the solar system entirely by the gravitational influence of passing stars as they are to remain bound to the Sun. Beyond this boundary lies interstellar space in the truest sense, territory that belongs to no star, governed by no single gravitational influence, where objects drift on trajectories shaped by the collective gravity of the galaxy, rather than by any individual stellar mass. The edge of the Oort cloud is, in the most meaningful physical sense, the edge of the solar system. Everything inside it, however loosely, however tenuously, is still gravitationally connected to our Sun. Everything outside it is not, and Voyager 1, silent by the 2030s, will spend 30,000 years crossing from where it currently sits to that true edge. By the time it exits the outer Oort cloud and enters the territory between stars in the fullest sense, the human civilization that built it will be as remote in time as the artist who painted the cave walls at Lascaux are from us today. No language spoken on Earth right now will survive in any recognizable form. No institution, no nation, no cultural tradition, with any traceable connection to the people and organizations that designed and launched and operated this spacecraft will exist. The name NASA will mean nothing to anyone if the concept of a name itself persists in any form we would recognize. The mission will have been forgotten not once but probably many times over, rediscovered perhaps as an archaeological curiosity, its context lost and partially reconstructed, and lost again across the intervening millennia, and still the spacecraft will be moving, outward, carrying its golden disk with Bach and whale songs and a heartbeat, and the brainwaves of a woman thinking about the cosmos, at 61,000 kilometers per hour, through a darkness that no human eye will ever see, toward the open galaxy. But the 30,000-year crossing is not the end of the story. It is not even close to the end. Because on the other side of that silence, in the open interstellar space beyond the Oort cloud, something is waiting. Not waiting intentionally, not aware of the appointment. But there nonetheless, in the mathematics, written into the trajectory from the moment of launch in 1977, a star, 40,000 years from now, and after that, the story stops having an ending at all. Part 9, the 30,000-year silence zone. There is a concept in geology called deep time, the idea that Earth's history operates on timescales so vast that human intuition simply cannot navigate them directly. When geologists talk about events happening over hundreds of millions of years, they are not being careless with numbers or speaking loosely for dramatic effect. They are working within a framework where 1 million years is a genuinely small interval, where the rise and fall of entire mountain ranges is a single chapter in a longer story, where the appearance and disappearance of entire species is a detail in the margins. Deep time is not a metaphor. It is a mode of thinking that had to be invented because ordinary human intuition, calibrated by evolution for timescales of years and decades, is simply not equipped to handle the actual age of things. Voyager 1's future, the journey it will continue after the last signal fades, requires something similar. Call it deep mission time. A framework for sitting with what this spacecraft will be doing across timescales that make all of recorded human history look not just small but invisible. After the last signal fades in the 2030s, after the antenna drifts or the power finally drops below the threshold, or the transmitter goes quiet for reasons the engineers at JPL may not be able to determine precisely, Voyager 1 will not stop. This point deserves more emphasis than it typically receives, because the cultural narrative around the end of the mission tends to treat the silence as a kind of ending. It is not an ending. The spacecraft will have been travelling at approximately 61,000 kilometers per hour since the moment of launch in September of 1977, and nothing in the environment it is moving through will change that in any meaningful way. The interstellar medium, as Voyager has itself confirmed through decades of measurement, is real and structured, but nowhere near dense enough to exert significant drag on a metal object moving through it. There is no friction in any practical sense. There is no resistance worth calculating on human timescales. In 1,000,000 years, Voyager 1's speed will have changed by an amount too small to be relevant to any description of its journey. It will keep going at essentially the speed it is going right now, through the silence, through the darkness, through the 30,000 years and beyond, without slowing, without stopping, without any force in its environment sufficient to bring it to rest. In roughly 300 years from now, around the year 2300, give or take the uncertainties in our models of the Oort cloud's inner boundary, Voyager 1 will begin entering the theoretical inner edge of the solar system's outermost structure. The spacecraft will not know this. There will be no instruments left to detect the transition, no power to run them if there were, no transmitter to report back what they found. The crossing of the inner Oort cloud boundary will be a purely physical event with no observer, no measurement, no record. The spacecraft will pass through whatever diffuse population of icy bodies occupies that region, without interaction of any kind, because the Oort cloud is distributed across a volume so enormous that even 1 trillion objects spread through it leave it, for all practical purposes, empty. This is not like passing through an asteroid belt, where the density of objects is high enough to be a navigation consideration. The Oort cloud is a volume of space containing approximately one object per tens of billions of cubic kilometers. Voyager 1 could spend the entire 30,000 year sailing through the geometric heart of the structure and never come within 1 billion kilometers of anything solid. The crossing will be total, unbroken, uninterrupted silence moving through theoretical space. The 30,000-year silence zone, the period between the last signal from the spacecraft and its eventual exit from the outer Oort cloud into true interstellar space, is where deep mission time becomes unavoidable as a concept. Because 30,000 years is not a large number in geological or astronomical terms, it is not impressive by the standards of deep time as geologists practice it. But it is a number that completely dismantles the human framework for thinking about legacy, memory, and the persistence of civilizations, and it does so in a way that is worth sitting with carefully rather than rushing past. Consider the last 10,000 years of Earth history and everything that fits inside them. The emergence of agriculture in multiple independent locations around the world, the domestication of horses, cattle, dogs, the invention of the wheel, the development of writing in Mesopotamia, in Egypt, in China, in Mesoamerica, independently, repeatedly, as though literacy were something the human brain was always trying to discover. The construction of Stonehenge, the pyramids at Giza, the Parthenon, the Colosseum, Notre Dame Cathedral, the Taj Mahal, the rise of Buddhism, Hinduism, Judaism, Christianity, Islam, the fall of Rome, the Black Death, the Renaissance, the Scientific Revolution, Galileo, Newton, Darwin, Einstein, the Industrial Revolution, the invention of electricity, of radio, of television, of computers, of the internet, of the smartphone in your pocket, 2 world wars, the moon landing, the sequencing of the human genome. Everything that any human being has ever written down, every scientific paper ever published, every novel ever printed, every song ever recorded, every mathematical proof ever derived, the entire intellectual, cultural, artistic, and scientific inheritance of our species fits inside 10,000 years. Voyager 1 will spend 3 times that span just crossing through the outer boundary of what we technically call the solar system. During those 30,000 years, Earth will not be holding still waiting for the crossing to end. The continents will have moved, not dramatically by geological standards, but measurably. The Atlantic a few hundred kilometers wider, the Himalayas slightly higher or lower, depending on the balance of uplift and erosion. The coastlines of every continent subtly reshaped by the slow grinding of tectonic plates. The climate will have cycled through multiple glacial and interglacial periods, ice sheets advancing and retreating across the northern continents, sea levels rising and falling, ecosystems reorganizing in response. The Sun will have aged by 30,000 years, genuinely imperceptible on stellar timescales, a rounding error in the life of a star expected to burn for another 5 billion years, but 30,000 years nonetheless, each one a real year in which the Sun fused real hydrogen into real helium and radiated real light onto a planet that was changing in ways its current inhabitants cannot predict. Species will evolve during those 30,000 years. Species will go extinct. The ecological relationships that currently structure life on Earth, the food webs, the pollinator networks, the ocean circulation patterns that distribute heat and nutrients around the planet, will shift in response to climate change, to habitat change, to the slow, ongoing process of evolution operating on every reproducing population simultaneously. Whatever occupies the ecological and cognitive niche currently held by human beings, whether that is biological humans who have changed through 30,000 years of evolution and cultural development, or their technological descendants in some form we cannot currently imagine, or something that emerged from human civilization and then diverged from it, or something that replaced it, will be living in a world as fundamentally different from today's as today's world is from the world of the last glacial maximum, when ice sheets covered much of the northern hemisphere and the ancestors of modern humans were still learning to paint on cave walls. And none of them will be listening to Voyager. Even if the spacecraft were somehow still transmitting, even if the physics of RTG decay worked differently and the power lasted, the signal would be so vanishingly faint at that distance, and the knowledge of how to receive and interpret it so specific to a particular era of technological and scientific development, that the capability would almost certainly have been lost and rediscovered and lost again many times over across 30,000 years of civilizational change. The deep space network, as a concept and as a physical infrastructure, will not exist. The protocols for communicating with 1970s era spacecraft will not exist. The institutional memory of the Voyager mission will not exist in any continuous form. Whatever intelligent beings inhabit the planet when the spacecraft exits the Oort cloud will have no more direct connection to the people who built it than we have to the humans who were alive when the last woolly mammoths were walking the Earth. What this produces is an object that fits into no existing category cleanly. Voyager 1, after the 2030s, will be a physical artifact of human civilization moving through space with no connection to any active human endeavour, no observer, no mission, no purpose in any operational sense. It will be neither lost nor found. It will simply be going, in the direction it was aimed in 1977, by specific people making specific choices, propagating those choices forward through time in the form of motion, long past the point where those choices can be revised or reconsidered, or even remembered by anyone. This is what it means to leave something behind in the truest sense. Not a monument that weathers and crumbles, not a record that burns or corrupts, but a direction, chosen once, that keeps going. Voyager 1 is human intent crystallized into velocity, moving through the dark on a heading set half a century ago, carrying the sounds of a world that will have transformed beyond recognition long before it reaches anything. And on the other side of the silence, on the far side of the 30,000-year crossing, something is waiting in the mathematics, not waiting with awareness, not waiting with intention. But there in the equations, locked in since launch day, as certain as orbital mechanics can make anything certain across 40,000 years of cosmic drift, a star is coming, and after that, the story stops having a horizon at all. Part 10. The Golden Record Paradox. Let us talk about the object on the side of this spacecraft that may be the most extraordinary thing humanity has ever made. Not the most technologically sophisticated. There are instruments and machines that surpass it by every engineering metric. Not the most scientifically significant. The data Voyager's instruments have returned about the heliosphere, and the interstellar medium will occupy researchers for decades. But the most extraordinary, in the sense of being the most complete and deliberate expression of what a species does when it looks out at the universe and feels, for the first time, the specific vertigo of being small but thinking large, of being one small, temporary thing in an incomprehensibly large and old place, and deciding that this fact is not a reason for silence, but a reason to speak as clearly and completely as possible, into the dark, regardless of whether anyone is listening. The Golden Record is a 12-inch gold-plated copper disc, encased in an aluminum protective cover, attached to the exterior of Voyager 1. It was designed under the leadership of Carl Sagan and a small committee of scientists, artists and thinkers, working in 1977 under significant time pressure, with the explicit intention of communicating the existence of intelligent life on Earth to any extraterrestrial intelligence that might someday intercept the spacecraft. The cover is not decorative. It is functional, a communication system in its own right, etched with instructions in a symbolic language designed to be interpretable from first principles by any intelligence capable of manipulating physical objects and understanding basic physics. The instructions include diagrams showing how to play the record, indicating the correct rotation speed using the period of the hydrogen atom's hyperfine transition as a universal unit of time. They include a pulsar map, a diagram showing the relative positions and pulse frequencies of 14 known pulsars, which function as a kind of cosmic address, uniquely identifying the location of our solar system within the galaxy to any civilization with sufficient astronomical knowledge to recognize the reference. They include a diagram of the hydrogen atom itself, the most abundant element in the universe, whose properties are the same everywhere in the cosmos, and can therefore serve as a shared starting point for any cross-species communication attempt. The people who designed this cover were not being naive. They were being as rigorous as the problem allowed. The challenge they set themselves: create a message interpretable by an intelligence with absolutely no prior knowledge of human language, human culture, human biology, or human physics, using only the universal constants of the physical universe as a bridge, is arguably the hardest communication design problem ever attempted. Whether they succeeded is a question that may never be answered, but the seriousness and care with which they approached it is evident in every detail of what they produced. What is on the record itself is, in many ways, a more interesting question than whether anyone will ever hear it, and it deserves more attention than the summary version of the story usually provides. The recording begins with 115 images encoded in audio, a technique that translates visual information into sound waves in a way that can be decoded back into images by anyone who understands the encoding scheme, which the cover instructions explain. These images show human anatomy in detail, including the biological systems that make us function. They show the structure of DNA, the molecular mechanism of heredity, the code that describes every living thing on Earth. They show the geography of our planet, the continents, the oceans, the patterns of land and water that define the world we live on. They show human beings in the context of their daily lives, eating, working, learning, caring for children, and in the context of their cultural expressions, music, art, architecture, ceremony. The selection of images was itself a years-long argument about what mattered most, what was most representative, what an alien intelligence would most need to see to understand what kind of creature had sent this message. The spoken greetings that follow are in 55 languages, ranging from contemporary major world languages to ancient tongues that were already dead in 1977, languages whose last native speakers had been gone for centuries, preserved here in recorded form because the committee decided that even extinct human languages deserved a place in this representation of what humanity is. The greeting in Sumerian, one of the oldest written languages in human history, was reconstructed from ancient texts specifically for this recording. A language that had not been spoken aloud in thousands of years was revived briefly, recorded, and launched into interstellar space. There is something about that specific detail, the resurrection of a dead language for inclusion on a message to the cosmos, that captures something essential about the ambition and the melancholy of the entire project. The sounds of Earth that follow the greetings are perhaps the most emotionally immediate part of the record for a human listener. Waves breaking on a shore, wind moving through trees, thunder, rain, the calls of birds, the sounds of frogs and insects on a quiet night, and then the sounds of whales, the long, complex, haunting vocalizations of humpback whales, recorded in the ocean, included because they represent another form of sophisticated communication on Earth, another example of a large-brained animal using sound to transmit meaning across distance. The heartbeat of a pregnant woman, recorded in a hospital, the laughter of a child. These are not scientific data points, they are emotional data points, included because the committee understood that what humanity is cannot be fully described by anatomy and geography. It requires the sound of a child laughing. It requires the ocean. The 90 minutes of music that follow represent one of the most extraordinary curatorial decisions in the history of human culture. Bach appears 3 times, the prelude and fugue in C major from the Well-Tempered Clavier, the gavotte from the Partita No. 3 for solo violin, and the second movement of Brandenburg Concerto No. 6. Beethoven's Cavatina from the String Quartet No. 13, the blues of Blind Willie Johnson, recorded in 1927, in a style that carries the full weight of human suffering and perseverance in its guitar lines. Chuck Berry's Johnny Be Good, a choice that generated some controversy at the time, with one NASA official reportedly suggesting that rock and roll was too adolescent for interstellar communication, to which Carl Sagan is said to have responded that there are a lot of adolescents on Earth. Georgian choral music, Azerbaijani folk music, Peruvian panpipes, an Indian classical raga performed by Kesabai Kerkar, an artist already in her 70s when the recording was made. Music from every inhabited continent spanning centuries of human musical development, selected not to represent the most sophisticated or the most popular, but to represent the breadth, the sheer range of what human beings have done with sound and time and emotion. And then there is Anne Druyan. She was the creative director of the Golden Record Project, a writer and thinker who would later become Carl Sagan's partner and collaborator. During the recording sessions, it was decided to include something that no message of this kind had ever attempted: the electrical activity of a human brain, recorded while its owner was engaged in deliberate, concentrated thought. Druyan sat with electrodes attached to her head and spent 45 minutes in a state of focused meditation, thinking specifically about the history of Earth, about the nature of human love and human suffering, about the existence of other possible intelligences in the universe, about what it meant to be alive and aware in a cosmos this old and this large. Her brainwaves were recorded, translated into audio, and included on the disc. She described the experience afterward as one of the most profound of her life. She was trying, she said, to compress everything important about being human into 45 minutes of sustained attention. Whether she succeeded is again a question without an answer. But the attempt, the idea that a human mind in the act of thinking about humanity is itself worth encoding and sending into the universe, is one of the most remarkable things anyone has ever done. The probability that any of this will ever be heard is, in strictly statistical terms, negligible. Voyager 1 is a small metal object moving through an incomprehensibly large volume of space. The probability of random intercept by any object over the next billion years approaches zero so closely that the distinction barely matters. Carl Sagan knew this. Everyone on the committee knew this. The Golden Record was not a naive project built on optimistic assumptions about extraterrestrial civilizations monitoring nearby space for incoming spacecraft. It was a deliberate choice to make the attempt regardless of the probability, because the people making it had concluded that the act of attempting communication has value independent of whether the communication is received. That meaning does not require an audience. That the whale songs and the Bach and the brain waves of a woman thinking about the cosmos are worth sending somewhere even if nowhere ever receives them, because they are real and they were ours. And the alternative, saying nothing, sending nothing, treating the silence as the appropriate response to the vastness, was, to these particular people, unacceptable. In 40,000 years, Voyager 1 will pass within about 1.6 light-years of Gliese 445, a red dwarf star in the constellation Camelopardalis. It will not slow down, it will not enter orbit, it will drift past at 61,000 kilometers per hour and continue outward. Whether anything in that system will notice is a question the probability chains make effectively unanswerable. But the record will be there, moving through the vicinity of another star, carrying the laughter of a child, and the brainwaves of a woman falling in love, and the 300-year-old blues of blind Willie Johnson, addressed to no one in particular, in a universe that may or may not be listening. The creators of this record did not send it because they expected it to arrive. They sent it because they could not bear the thought of leaving without saying something. And that fact, that specific, irreducible human fact, may be the most important thing the Golden Record communicates, even if no one ever plays it. Part 11. Voyager and the mind that outgrew its maker. There is a parallel unfolding right now on Earth that the Voyager story illuminates in a way that no other metaphor quite manages. It is not a perfect parallel. No metaphor drawn from a single spacecraft drifting through interstellar space is going to map cleanly onto the full complexity of what is happening in technology right now. But the structural resemblance is close enough and specific enough that ignoring it feels like a deliberate choice to look away from something important. We are currently in the middle of the fastest technological transition in human history, faster than the Industrial Revolution, faster than the electrification of the world, faster than the emergence of the Internet, and the defining feature of this transition is not the raw power of the technology being built. It is our relationship to it. Specifically, our increasing difficulty maintaining meaningful, practical oversight over systems that operate faster, at greater scale, and across more domains simultaneously than human cognition can track in anything approaching real time. Voyager 1 has been effectively beyond real-time human control for years. This is not a failure of mission management or a design flaw. It is a direct consequence of physics. The speed of light is approximately 300,000 kilometers per second, and Voyager 1 is currently about 25.8 billion kilometers away, which means a signal traveling at the speed of light takes more than 23 hours to make the one-way trip. The round-trip communication delay already exceeds 46 hours and grows longer every day. When the mission team at JPL sends a command to the spacecraft, they are not pressing a button and watching something happen. They are composing an instruction, transmitting it across a day of space, and then waiting another day to find out whether it worked. In the interim, the spacecraft operates on its pre-programmed sequences, executing instructions autonomously, making no decisions in any sophisticated sense, but also receiving no real-time guidance. Human intervention is possible but slow, deliberate, and always based on information that is at minimum 23 hours stale. The mission team does not control Voyager in the way the word control usually implies, with immediate feedback, real-time adjustment, the ability to respond to changing conditions as they develop. They manage it from a distance, across a time gap, relying on predictive models and careful advanced planning rather than anything resembling live oversight. Now hold that picture in mind and consider what is happening with large-scale artificial intelligence systems right now, today, on Earth. These systems operate at speeds that are not just faster than human deliberation, but faster by many orders of magnitude, millions or billions of operations per second, processing information and generating outputs at rates that no human observer can follow in real time, regardless of how carefully they are watching. They make consequential decisions continuously. In financial markets, where algorithmic trading systems execute transactions in microseconds based on pattern recognition that no individual human could replicate. In content recommendation systems, where the specific videos and articles and posts that hundreds of millions of people see every day are selected by models whose internal reasoning is not fully transparent even to their creators. In infrastructure management, in medical diagnostic support, in legal document review, in hiring pipelines, in credit assessment, across an expanding range of domains where the speed and scale of automated decision-making have already outpaced any practical model of individual human review for each decision made. The feedback loops in these systems are short in clock time, but their cumulative effects accumulate faster than any individual human observer can track across the full scope of the system's operation. We are increasingly in a situation where the systems we have built are not exactly beyond our control. We can still turn them off, still update them, still set their parameters and define their objectives, but are operating in a regime where real-time human oversight of individual decisions is effectively a procedural fiction. We maintain the language of control and the organizational structures associated with it, but the practical reality of what oversight means when a system is making millions of decisions per second across a global user base is genuinely different from what oversight meant when the decisions were made by people at a pace people could monitor. Voyager 1 is, in this light, a very early and very simple prototype of a question that is now becoming one of the central questions of technological civilization. What does it mean to build something and then lose, not through negligence or failure, but through the inherent logic of scale and speed and distance? The ability to course-correct it in real time. For Voyager, the mechanism of that loss is the speed of light, which is a hard physical limit that no engineering can overcome. For AI systems, the equivalent constraint is different in its nature. It is the speed of computation combined with the complexity of the systems involved, which together create a practical gap between human intention and system behavior that grows larger as the systems become more capable and more widely deployed. The gap is not infinite, it is not unbridgeable in principle, but it is real, and it is growing, and the history of the Voyager mission offers one of the most detailed long-term case studies we have of what it looks like to manage a consequential system operating beyond the reach of real-time human intervention. What that case study shows is not reassuring in a simple way, but it is instructive in a useful one. The JPL team managing Voyager cannot steer the spacecraft in real time, so over decades they developed a different mode of operation entirely. They plan exhaustively in advance, modelling the spacecraft's expected behaviour across extended time horizons, and writing command sequences robust enough to handle anticipated variations without requiring mid-sequence human intervention. They maintain extraordinarily detailed institutional knowledge about the spacecraft's specific behaviours, quirks, and failure modes, knowledge that lives not just in documentation, but in the minds of the engineers who have spent careers developing intuitions about how this particular machine responds to particular conditions. They monitor telemetry continuously, not to catch problems as they happen, but to detect the early signatures of developing issues before they become critical. And they have cultivated over 46 years a specific kind of organizational patience, the willingness to work on timescales measured in days and weeks rather than minutes and hours, to accept that some problems will take a long time to diagnose and a longer time to fix, and to treat that slowness not as a failure of the system, but as an inherent feature of the operating environment that good management has to account for. This is not a perfect system. The 2023 memory corruption event demonstrated its limits with uncomfortable clarity. A single cosmic ray struck a single memory chip, corrupted a small section of data storage, and produced months of garbled telemetry that took the team weeks to diagnose and months to fix, all across a communication channel where every exchange consumed nearly 2 days of round-trip time. The recovery succeeded. But it succeeded narrowly, and it succeeded because the corruption happened to affect a section of memory that could be worked around through software rather than a piece of hardware that could not be replaced or bypassed. The next event may not be so accommodating. The system worked this time, in this specific instance, through the combination of deep expertise and reasonable fortune. That combination has held for 46 years. There is no guarantee it holds for 5 more. But the imperfect success itself contains a lesson that is worth stating directly, because it tends to get lost in discussions of AI oversight that oscillate between techno-optimism and existential alarm without spending much time in the space of practical operational wisdom. The lesson is not that we can always recover from unexpected failures in complex autonomous systems operating beyond real-time human control. We cannot always recover. Sometimes the failure mode is one that cannot be patched around. Sometimes the cosmic ray hits the wrong chip. The lesson is that the combination of careful advanced design, sustained institutional vigilance, and deep domain expertise can extend the period of reliable operation far beyond what the original engineering margin suggested was possible, and that the people responsible for maintaining those qualities over long time scales, who keep paying close attention long after the exciting early phase of the mission is over, are as important to the ultimate outcome as the engineers who built the system in the first place. The distance Voyager 1 has covered, all 25.8 billion kilometers of it, every AU travelled, every record broken, every scientific measurement returned, was not produced by a single inspired engineering decision made in the 1970s. It was produced by 46 years of continuous human attention, by generations of mission controllers and engineers choosing to keep paying attention to a machine that was getting harder and harder to hear, that was operating in conditions no one had ever encountered before, that was failing in slow and subtle ways that required careful watching to even detect. The achievement is not just the spacecraft. The achievement is the attention. That is worth sitting with as we try to work out what kind of attention we owe to the systems we're building now. Systems that are, in some meaningful ways, already further from real-time human oversight than Voyager 1 was in its first decade of operation. Systems whose consequences accumulate faster, whose failure modes are less well characterized, and whose operating environment, the social and economic and informational fabric of human civilization, is considerably more complex than the interstellar medium. We built Voyager and kept watching it for nearly half a century. The question of how long we are prepared to keep watching the things we are building now, and how carefully, is not a technical question. It is a question about what we value and what we are willing to sustain, and the answer we give to it will matter for longer than any of us will be around to see. Part 12. The Last Signal and What Comes After. We are now in a position to trace the full arc of this story, from the fading signal of the 2030s to the end of everything we currently understand about the universe, and to sit with the question of why a spacecraft the size of a small car, launched on September the 5th, 1977, by a species that had only been spacefaring for 20 years, might be one of the most important objects in the history of the universe's awareness of itself. That is a large claim. It deserves to be earned rather than simply asserted. So let us follow the trajectory all the way to the end and see whether the claim holds. The signal will fade. Sometime in the early to mid-2030s, the precise timing dependent on variables that cannot be predicted with certainty from here, including the rate of thermoelectric degradation, the stability of the attitude control system, and whether any additional cosmic ray events compromise critical hardware before the power budget, makes the question moot. The last coherent telemetry from Voyager 1 will arrive at one of the Deep Space Network's antenna arrays. The engineers on duty will analyze it the way they analyze every packet of data that comes in, carefully, methodically, comparing it against expected values and looking for anomalies. If contact is lost suddenly, They will attempt recovery. They will send commands. They will wait 46 hours for responses that may not come. They will try different approaches, different frequencies, different pointing corrections, working through the checklist of possible causes with the patience that 46 years of managing this spacecraft has instilled in the people who do this work. And at some point, perhaps after days of attempts, perhaps after weeks, they will conclude, with the particular quiet that comes from certainty arriving slowly, that the spacecraft is no longer transmitting in any way that can be recovered. The mission will be formally ended. There will be statements from NASA, tributes from scientists around the world, retrospectives in every publication that covers space. The people who devoted careers, in some cases entire careers, decades of professional life to listening across 25 billion kilometers of space, will sit with the silence in whatever way people sit with the end of something that mattered enormously. And then, because this is how institutional time works, the file will be closed. The Deep Space Network will redirect its attention to the missions that are still active, still transmitting, still generating data that requires analysis. The offices at JPL where Voyager was managed will be reassigned. The specific expertise accumulated over 46 years of flying the most distant spacecraft ever built will begin, slowly and irreversibly, to disperse. And Voyager 1, alone in the interstellar medium, will keep going. At 61,000 kilometers per hour, it will continue outward without interruption, without deceleration, without any awareness of the silence that has fallen on the other end of the connection. In roughly 300 years, it will cross the theoretical inner boundary of the Oort cloud, entering the loosely defined outermost region of the solar system, with no instruments to register the transition and no transmitter to report it. It will spend 30,000 years crossing that structure, 30,000 years of moving through a diffuse population of icy bodies so spread across such an enormous volume that the probability of encountering any of them approaches zero, and then it will exit the other side into the true interstellar void, the space between stars in the fullest sense, the territory that belongs to no sun. By that point, no human language spoken today will exist in any recognizable form. No institution with any traceable connection to NASA or to the United States or to the civilization that built this spacecraft will persist. The mission will have been forgotten and rediscovered and forgotten again, its context reconstructed imperfectly from whatever records survive, the names of the people who built and flew it preserved perhaps in historical archives, but disconnected from any living tradition that remembers why they mattered. In 40,000 years, the trajectory locked in at launch will bring Voyager 1 within approximately 1.6 light-years of Gliese 445, a red dwarf star in the constellation Camelopardalis. The spacecraft will not slow down. It will not enter orbit. It will pass through the vicinity of another star system at 61,000 kilometers per hour, the golden record on its side carrying Bach and whale songs and a heartbeat, and the brain waves of a woman thinking about the cosmos, and then continue outward into the open galaxy without pausing. Whether anything in that system notices the passage is a question whose answer we will never know from here. In 100,000 years, the stars visible from Voyager 1's position will be arranged differently than they are now. The proper motions of nearby stars, their slow drift across the sky relative to one another, driven by their individual velocities through the galaxy, will have accumulated over 100 millennia into a completely different stellar neighborhood. The constellations that human beings have named and navigated by and told stories about for thousands of years will be unrecognizable configurations of light. The night sky that Voyager 1 would see, if it had eyes, will bear no resemblance to the night sky that the people who launched it looked up at in 1977. In a million years, the orbital mechanics that shaped Voyager's trajectory through the solar system, the careful gravity assists off Jupiter and Saturn that gave it the speed to reach interstellar space in a human lifetime, rather than a geological one, will be entirely irrelevant to its motion. It will be a free drifter on galactic scales, its path determined not by the gravity of any individual star, but by the collective gravitational field of the entire Milky Way galaxy. The combined pull of 200 to 400 billion stars acting on a metal object massing less than a metric ton. It will be, in the truest sense, a galactic object rather than a solar system object. It will belong to the galaxy, the way a leaf carried out to sea eventually belongs to the ocean rather than to the river that carried it. In approximately 4 to 5 billion years, a timescale that encompasses the entire remaining main sequence lifetime of our Sun before it exhausts its hydrogen fuel and begins the expansion into a red giant that will eventually consume the inner planets, the Milky Way will have completed its long-anticipated collision and merger with the Andromeda Galaxy. This is not a speculative future event. It is a prediction with high confidence, based on precise measurements of Andromeda's velocity and trajectory toward us. The two galaxies are currently approaching each other at roughly 110 kilometers per second, and in 4 to 5 billion years they will interpenetrate in a slow-motion collision that will, over the course of several billion additional years, produce a merged elliptical galaxy that astronomers have already informally named Milkomeda. The stars within each galaxy are so widely spaced that direct stellar collisions will be rare, but the gravitational dynamics of the merger will scramble the orbital structure of both galaxies, sending stars on new trajectories, reorganizing the stellar geography of everything we currently recognize as our cosmic neighborhood. Voyager 1 will be somewhere in that merged galaxy, still moving, still intact. In the broad structural sense, the metal of its frame corroded in ways that billions of years of exposure to interstellar radiation and cosmic rays will produce, but structurally present, a coherent object rather than dispersed debris, still carrying the golden record. The gold plating on the record's cover is expected to survive for at least several billion years under the conditions of interstellar space. The copper disk beneath it will survive longer still. The information encoded in its grooves, the images, the greetings, the music, the sounds of Earth, the brainwaves, will still be physically present, still readable in principle by anything with the right technology and the motivation to look. Bach will still be there. The heartbeat will still be there. The electrical signature of Andruin's mind, thinking about what it means to be alive in a universe this large, will still be encoded in the microscopic geometry of a gold-plated copper disk, drifting through a merged galaxy that contains no memory of the civilization that put it there. At this scale of time, the question of whether any intelligence will ever find the record and hear it becomes genuinely different from what it is today. 1 billion years is long enough for stars to form from interstellar gas, for rocky planets to cool and develop liquid water, for chemistry to organize itself into biology, for biology to develop complexity, for complexity to develop cognition, for cognition to develop technology. If the universe is as generative of life as our rapidly growing catalogue of exoplanets is beginning to suggest, if the thousands of Earth-sized planets in habitable zones that we have already found represent a cosmos that makes life routinely rather than rarely, then the probability that at least one intelligence capable of detecting and retrieving a drifting spacecraft will arise somewhere within potential intercept range over the next billion years is not the effectively zero figure it is over human timescales. It is something more interesting than that, something that resists easy dismissal. But the thought worth leaving you with is not about the probability of reception. It is about what the record means regardless of whether it is ever received. The meaning is already fully present in the object. It is in the choice to put whale songs next to Bach, the implicit statement that sophisticated communication on Earth is not exclusively human. It is in the encoded brainwaves of a person trying to compress everything important about consciousness into 45 minutes of sustained attention, the implicit statement that inner experience is as real and as worth transmitting as external fact. It is in the 55 spoken greetings in languages, including ones already dead when the record was made, the implicit statement that every human attempt at language, every human effort to mean something to another person, deserves to be represented here. Every choice was an act of self-definition. A species, young enough to still be surprised by its own existence, looking at itself carefully and asking, what are we, really, and how do we say that in a form that might last? The universe will proceed without us. It was proceeding for 13.8 billion years before we arrived, and it will proceed for an unimaginable duration after every trace of us has faded. It does not need our mark. It didn't ask for it. But we made it anyway. This small, fragile, extraordinary object, aimed at the dark between stars with music on its side and a pulsar map on its cover, and the brainwaves of a woman falling in love encoded in its grooves. We made it and launched it and listened to it for 46 years across distances that still seem impossible, and it is still out there, still whispering, barely above the noise, telling us what it found in the space we will never reach ourselves. The signal is almost gone. The distance it will cover before it dies is the kind of number that restructures your sense of scale. The distance it will cover after, measured not in years or centuries but in the remaining lifetime of galaxies, will do something quieter and more lasting than that. If you let it, it will make you feel the specific, unrepeatable privilege of being alive right now, in this thin sliver of cosmic time, when the most distant thing our species has ever made is still close enough to hear.